In Chapter 8, we will learn about sequences and series. The main focus of this entire chapter and the next one is this series, but in order to understand series, we need to first talk about sequences, and they're very similar. So a sequence which has notation, a curly brace, a sub n, and close your curly brace, is just an ordered list of numbers. The curly braces in that notation represent the fact that we're creating an entire set of numbers. And A is just the name for this sequence. The subscript n is called the index, and it tells us what term of the sequence we're talking about. So we will typically be given, very much like a function, we will be given some expression for a sub n that we could use to generate the terms of a sequence. And if we do that, the one thing, one of the major ways that a sequence differs from a function is that with sequences, you always start off by plugging in 1, and then from there, you just increase, and you're only allowed to use whole numbers. So the first term of the sequence is a sub 1, the second term of the sequence is a sub 2, and so on. And the way that we get these terms is by plugging those subscripts into the expression for our sequence. So for the first term, we're plugging in 1. For the second term, we're plugging in 2, and so on. A few examples of what these sequences will look like. We may be told that a sub n is 5n minus 1 all over 2 to the n factorial. If you don't know what factorials are, that's fine. We will cover that in just a little bit. So what we've said here is that A is the name for this sequence. N is the index, which means N is kind of like the variable that we're using. And to get the first term, we'd plug in n equals 1. To get the second term, we'd plug in n equals 2. So the 5n minus 1 over 2n factorial is an explicit formula for how we calculate the terms of this sequence. Another example for a sequence, negative 1 to the n over n squared. So just a different name. This sequence is called B. We're always going to use n as our index, which is our variable, and the negative 1 to the n over n squared tells us how to generate the terms for this sequence. So one of the things that's important for us to learn how to do in this section is to generate some terms in a sequence. So for this first example, we're going to generate the first 4 terms of the given sequence. And the first term that we're going to look at, a sub n equals 2n over n squared plus 3. So this is going to create a set of numbers. For sequences, we always start with n equals 1. We're not allowed to plug in negative numbers. We're not allowed to plug in decimals or fractions. We have to start with 1 and then just continue with the whole numbers above 1. So the first term, we would plug in 1 for n, and we get 2 in our numerator. If we plug in 1 in the denominator, 1 squared is 1 plus 3 is 4. So we get 2 over 4, which simplifies to a half. That would be the first term of our sequence. This is equivalent to the a sub 1 that we talked about in the definition. If we plug 2 in, we're going to get 4 in the top. 2 times 2 is 4. In the bottom, 2 squared is 4 plus 3 is 7. So a sub 2 is 4/7. If we plug in 3, we'll get 6 in the top. And then the denominator, 3 squared is 9 plus 3 more is 12. So we get 6 over 12. So we get a half again. And then we were just asked for the first 4 terms, so we're just going to do one more. 2 times 4 is 8. 4 squared is 16, plus 3 more is 19. So this sequence would continue on forever, all the way to infinity, but those would be our first 4 terms. So we'll look at another one really quickly. This time we have 3 times negative 1 to the n all over 2n minus 1. We're going to see this negative 1 to the n come back a lot, and once we write out the terms here, it will be easy to see exactly what purpose that negative 1 to the n is going to serve. So for the first 4 terms, we have to start by plugging in 1. So in our denominator, we get 2 times 1 minus 1, which is just 1. In our numerator, we have negative 1 to the first power, which is a negative 1. So overall, we get negative 3 over 1, which is negative 3. That is b sub 1, because the name of this sequence is b, and negative 3 is what I get back from my sequence when I plug 1 in. If we plug in 2, in the denominator, I get 4 minus 1, which is 3. And negative 1 squared is positive 1. So I get positive 3 over 3, which is 1. That's our b sub 2. If we plug 3 in, we get 5 in the bottom, and negative 1 cubed is negative 1. So we have negative 3 over 5. And then finally, if we plug in 4, negative 1 to the 4th power is a positive 1. So we get 3 over 2 times 4 is 8 minus 1 is 7. So 3/7. And we could continue this forever if we wanted to, but we're just asked for 4 terms. So what we're seeing here is every time we have this negative 1 to the n power, it was causing the signs on our terms to flip-flop back and forth between positives and negatives. And this is called an alternating sequence. Anytime the signs of your terms consistently alternate back and forth between positive and negative, we call that an alternating sequence. We'll also see that when we start talking about series, and that name will still hold. It would still be considered alternating. So anytime we see a negative 1 to the n power used in the expression for our sequence, we know that our terms are going to be alternating. Probably the most important thing of this whole section, and for understanding understanding sequences, is being able to find the limit of a sequence. And the limit for a sequence, we work the exact same way we do the limit for a function, like in Calculus 1. The one nice thing about limits of a sequence is we are only concerned about n approaching positive infinity. So we don't have to worry about discontinuous functions and our variable approaching a specific number, or ever going to negative infinity either. The only thing we're interested in is if we were to extend these terms out forever, would they eventually fall into a pattern and approach a single number? So the limit as n approaches infinity for a sub n is called the limit of a sequence. And sometimes we get an actual number back. But you might remember there's also times from Calculus 1 where we tried to take a limit and our answer was does not exist, or the answer was positive or negative infinity. And I'm sorry, my pen is not working. So to calculate these limits, we don't really have to learn anything new. We just remember how we did limits back in Calculus 1. So the limit as n approaches infinity for a sequence would be exactly the same as the limit as x approaches infinity for some function where f sub n would give us our sequence. If we were to go into that function and replace the x's with n's, it would look exactly the same as what our sequence looks like. Before we do this next example, let me give you a little bit of terminology. If the limit is some finite number, L, then we say that this sequence converges. But if for some reason the limit does not exist, or we get positive or negative infinity, then we say that the sequence diverges. We would never answer a limit question with positive or negative infinity. That just means that the sequence diverges. And that would be our answer. We would say diverges. So we're going to try to find the limit of a couple of sequences. And how we do that is not new. Like I said, it's exactly the same way we did it in Calculus 1. If for some reason we can't find the limit, that means it diverges. So we want to find the limit of each sequence, or state that the sequence diverges. So let's say our first sequence, a sub n, is 5n minus 1 over n squared plus 2. You could also think of this as the function 5x minus 1 over x squared plus 2. This function, if we plug the correct numbers in, would give us back the exact same values that we have in our sequence. Now the trick with the sequence is we start with 1 for n, and then we can only plug in whole numbers that come after that. If you remember back to algebra, for f of x, we could pretty much plug in anything we wanted. We could plug in negatives, we can plug in decimals, we could plug in fractions. But just for the sake of comparison, we could think of this as a function as long as we just stick to the numbers that we are allowed to plug in. So the way that we would work a limit like this, there's a very kind of technical analytic way to do it, but there's also a shortcut. And this only works for rational expressions. A rational expression is a fraction that has polynomials on the top and the bottom. So if we know we're working with a rational expression, what we need to do is compare the degree of the polynomial in your numerator to the degree of the polynomial in the denominator. And I'm going to call the degree of my numerator capital N, and the degree of my denominator capital D. And depending on how these two relate to one another, we can decide exactly what that limit's going to be. If the degree in your numerator is larger than the degree in your denominator, then our series is going to diverge. When we compare those degrees, that larger degree in our numerator is going to get faster, much quicker than the numbers in the denominator. So the values in our sequence are just going to get larger and larger and larger forever. If the degree in the denominator is bigger, then a sub n converges to 0. If you think about a fraction whose denominator continuously gets larger and larger and larger much quicker than the numerator, the values of those fractions are just going to get smaller and smaller and smaller and eventually go to 0. If those degrees are equal, then the limit is the ratio of your leading coefficients. The leading coefficients are the coefficients on the term that has the largest exponent. And because this will always be a finite number, that means these types of rational expressions are also going to be considered convergent. So with this in mind, let's look back at the problem we were just asked to do. We've got 5n minus 1 over n squared plus 2. So if we compare the degree of our denominator, which is 2, with the degree of our numerator, if we see a variable but there's no exponent written, that means it's an understood 1. So we've got d equals 2, n equals 1. So d is larger than n. That means this limit is 0. The limit as n approaches infinity for a sub n is 0. So if we were to write out the terms for this sequence, write out 10 or 20 or 30 terms, we would see that the value of those terms get smaller and smaller and smaller, and will eventually get really close to 0. So let's look at another one real quick. B sub n is negative n cubed over 2n plus 5. Again, it's a rational expression. Here, the degree of our numerator is 3. The degree of the denominator is 1. Since the degree of the numerator is larger, we would say that this sequence diverges. If you were to write out the values, or the terms of that sequence, they would just keep getting larger and larger and larger and larger without ever approaching a single number. Another one real quick. C sub n is equal to 2n plus 1 over 3n minus 5. Here, the degree of our numerator is 1, the degree of our denominator is 1, and we said when they were equal, what we would have to do is look at the ratio of the leading coefficients. So the numerator and denominator are growing at the same rate. The one thing that will always be true about them is that the numerator grows by doubling the n, the denominator grows by tripling the n, so eventually, as n gets larger and larger and larger, that plus 1 and minus 5 are not going to make any difference. If you think about plugging in 1,000 for n, adding 1 to 1,000 doesn't make a whole lot of difference, or 10,000, or 100,000, or 1,000,000. All that really matters is that coefficient, because that coefficient will double it or triple it. And the values of these terms, as n gets larger and larger and larger, are going to approach 2/3. Now, we don't have to say that this sequence converges. By being able to identify a limit, that automatically means that it converges. If we can't find a limit, then we would say diverges. There is a theorem, which is like a rule, that can guarantee us that a sequence will converge if a sequence a sub n is monotonic and bounded, then a sub n is convergent. Now, it doesn't tell us what it converges to, but it just guarantees that it will be convergent. So there are some words in here that we should talk about what they mean, the monotonic and the bounded. Monotonic means that the terms of a sequence are always moving in one direction. They're either always getting larger or they're always getting smaller. So the alternating sequence we saw earlier would not be monotonic because it keeps jumping back and forth between positive and negative. And it really doesn't matter whether the terms are always getting larger or always getting smaller. Both cases are considered monotonic. There is a way that you can check monotonicity of a sequence without having to generate a whole bunch of terms. So, like we said earlier, a sequence could also just kind of be considered a specialized function where we have very strict rules on what we can use for input. In Calculus 1, you learned that f prime of x can be used to determine if a function is increasing or decreasing. So if f prime of x is always positive, that meant that the function was increasing. If f prime of x was always negative, then it was always decreasing. Most likely in the problems you saw in Calculus 1, we had to determine specific intervals where the function was either increasing or decreasing. But in order to be monotonic, what we're looking for is f prime to always be positive or always be negative. If there's a chance that it could flip-flop back and forth between the two, then our sequence would not be monotonic. It would have areas where it was increasing, and then it would have other areas where it was decreasing. So that other key word in there was bounded. And bounded means that all of the values of the sequence, all of the terms of the sequence, stay within a specific range. Or a specific interval. So if we could identify a value that the terms never get larger than, so these sequences are bounded above, we're able to find a value that the terms are never capable of reaching. And they're bounded below, which means we're able to find a value that is always less than our terms. So if our sequence is bounded above and bounded below, that means that overall we could just say it is bounded, that all of the values stay within a specific range. There's a way that you can graph a sequence on your calculator if you go to Mode and change it to sequential. Most likely it's in function mode right now, but you can change it to sequential mode or sequence mode, and you can look at a graphical representation of the terms in your sequence. And sometimes that's an easy way to determine if your sequence is bounded or not. So a sub n is 2n minus 1 over n squared. And I'm going to plot out the terms for this sequence. So remember, sequences always start with n equals 1. If I were to plug 1 in, I would get back 1. And don't expect to see a graph when you do this on your calculator. A sequence is not a graph. A sequence is just a series of specific values. And it would not make sense for us to connect them because the next value I'm allowed to plug in is 2. So there's going to be a big gap. We're not allowed to plug in the decimals and fractions in between, which means we can't connect the 2 points. But if we were to plug 1 in, we would get 3/4. So that's just a little bit smaller. If we plug 3 in, we would get 5/9, which again is a little bit smaller. If we plug 4 in, we get 7/16, even smaller. If we plug 5 in, we get 9/25. These values are getting smaller and smaller and smaller, but they're staying positive. There's nothing in this expression that would ever make our terms go negative. If you plug in 6, you're going to get 11/36, which is less than 1/3. If you plug in 7, you're going to get 13/49. Plug in 8, you're going to get 15/64. So we can see the trend of these terms. They're always going down. That would mean that the sequence is monotonic. These terms are always decreasing, and they are bounded. The largest we'll ever get is 1. So we can pick any value, say n equal, or say 2. Our sequence will never get up to 2. So we could say that this sequence is bounded above by 2. And it looks like we can't ever get 0 out of this fraction either. But the terms keep getting closer and closer and closer and closer. So I could say that my terms will never get down to -1. There's other numbers you can use for those bounds, but I know for certain that my terms will never go above 2, they'll never go below -1, and this sequence is decreasing, so it's monotonic. We can check that algebraically by thinking of this as a function, 2x minus 1 over x squared, and calculating our derivative. We're going to have to do a quotient rule. So the quotient rule says start with the derivative of the top, and multiply that by the original bottom, minus the top times the derivative of the bottom. So 2x minus 1 times 2x, all over the bottom squared, which would be x to the 4th. And if we simplify this a little bit, I'm going to have 2x squared minus 4x squared plus 2x. So negative 2x squared plus 2x over x to the 4th. We can simplify a little bit further because everything has an x in it. So this is negative 2x plus 2 over x cubed. Now this is our derivative, and we can show that if we start with a value of 1 and increase from there, this is always going to be negative. X cubed will always be positive because remember, for the sequence we're only allowed to plug in values from 1 to infinity, just the whole numbers. So if you take a positive number and you cubed it, you're always going to get back a positive number. And then besides what's happening at 1, if we plug in n equals 1 or x equals 1, we'll get 0. But everything after that, if you plug in 2, 3, 4, 5, 6, this number in the front is going to be bigger than the number in the back, which is going to result in a net negative value. And anytime you have a negative divided by a positive, you get a negative. So the terms of this sequence are always decreasing. It is monotonic, and we also showed that it's bounded, and that proves that it must have a limit. It doesn't exactly tell us how to find it, but it proves that it does have one. The last very important thing that we need to understand about sequences before we can move on to series is if we're just given the terms of a sequence, we want to be able to come up with the equation or the expression for the sequence. It's much easier to calculate the exact limit from the expression than it is just from an incomplete list of terms. So we call that the nth term, finding the nth term of a sequence, because it's the expression that we have our n in, our index, telling us how to generate the terms. So there's a lot of patterns that you might see, and we'll take a look at each of them and we'll talk exactly about how we translate those into an expression. So first let's look at some example patterns. 2 times n, if we had that as our sequence, this would give us 2, 4, 6, 8, 10, because we keep plugging in larger and larger values for n, and all it's going to do is multiply it by 2. So one thing you should notice here is that every single time we jump from one term to the next, we're just adding 2. So anytime you see that there is a common difference in each of your terms, that's going to translate into multiplication in your sequence. we could also have some addition or subtraction on that sequence. So if we started with 1 here in 3n minus 2, we would get 1. If we plugged in 2, we'd get 4. If we plugged in 3, we'd get 7, and then 10, and then 13. And if you check what's happening from term to term, every time we're adding 3. So there is a common difference between each of the terms. That common difference is going to translate into multiplication. And then you can look at your first term to see if that multiplication needs to be adjusted. If we only used 3n, that means our first term should be 3. But ours isn't, it's 1. So this entire sequence got shifted down 2 in order to move 3n from 3 down to 1 as our first term. We'd have to subtract 2. So anytime you see a common difference, it's going to translate into multiplication, and then you should check your first term to see if it matches up with your expression. If not, we might have to add or subtract to adjust it. You might also see exponential expressions. So if we had, let's say, 4 to the n. If you start plugging in the values of n that you're allowed to, you'd get 4, 16, 64, 256. And it's obvious just by looking at this that they're not going to have a common difference. To jump from 4 to 16, I only have to have 12, add 12. But to jump from 64 to 256, we've got to add like 192, it looks like. So they don't have a common difference. So the other thing you can check is if they have a common ratio. And that means I'm multiplying by the same number every time to jump from one term to the next. And that's the case here. Once you have your first term, to get to the next, you multiply by 4. To get to the next, you multiply by 4. Get to the next, you multiply by 4. Anytime we see that common ratio, what we have is our base for an exponential. N squared also has a pattern. It's not quite as obvious though. If we generate some terms in the n squared sequence, we'll get 1, 4, 9, 16, 25. Now these might be pretty easy to recognize, but what if I asked you for the expression for 3, 6, 11, 18, 27? You wouldn't necessarily recognize that I generated that using squares. So the trick to recognize a square is we are adding increasing odd numbers every time. The way we get from one term to the next is we add the next larger odd. And that pattern will translate to other more complicated sequences. So to go from 3 to 6, I have to add 3. To go from 6 to 11, I have to add 5. 11 to 18, add 7. 18 to 27, add 9. So I'm seeing the exact same pattern here. The only difference is the first number got adjusted up 2 units. And that's actually true for all of these if you compare them. So we are dealing with the n squared pattern, but we just pushed everything forward 2 units. So we'd get n squared plus 2. We might also see, usually not all by itself, but just as part of an expression for a sequence, -1 to the n or -1 to the n plus 1. So remember, n has to start at a value of 1. So for -1 to the n, we start off negative, and then we're flip-flopping back and forth between negative and positive over and over and over again. If you start with n equals 1 on the second one, we really start with an exponent of 2, and that's going to start us off positive. So both of these expressions represent an alternating sequence, but we could adjust and use either n or n plus 1 depending on if we want our first term to start off positive or negative. But both of these are a clue, if we see them in our sequence, to let us know that we're dealing with an alternating pattern, or an alternating sequence. One more pattern really quick I want to show you is factorial. And before I write out the actual terms, I need to tell you what factorial means. By definition, 0 factorial is equal to 1. Every single value higher than that, we can't do factorials of negatives, we can't do factorials of decimals, so the rule for factorial lines up very nicely with the rule for sequences. We do need to know what 0 factorial is in case there was any up or down adjustment of the n. But the rule for finding a factorial is you start with the number they gave you and you multiply it by every whole number that's less than it until you get down to 1. So 5 factorial, that means we need to calculate 5 times 4 times 3 times 2 times 1, which is 120. 3 factorial. These values get big really fast, so I don't want to do anything too giant. That just means 3, you start with the number they gave you, and then multiply it by all those whole numbers that are smaller until you get down to 1. 3 factorial is just equal to 6. So if we were to do this for all of the numbers that we were allowed to plug into a sequence, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120. Now, this might be a sequence that's really hard to recognize unless you memorize those specific values. But just kind of like our squared, once we looked at the common difference, we were able to recognize a pattern. With these, you are going to see a common, or not a common ratio, but a pattern in the ratios. To multiply from 1 to get to 2, you have to multiply by 2. To go from 2 to 6, you have to multiply by 3. To go from 6 to 24, we have to multiply by 4. To go from 24 to 120, we have to multiply by 5. So it's not that we have a common ratio, but there is a pattern in what we are multiplying by to get these values. So if we see that pattern, it's a factorial. So we're going to do 2 quick examples. We want to find the nth term. What we're going to be given is just some of the terms in the sequence, and we want to be able to write out the expression that was used to generate those terms. For our first example, we've got 3, 7, 11, 15, 19, and so on. And what we want to do is write out the nth term for the sequence, which means we want to find an expression that will generate these terms. So remember some of the things we looked for. I don't see any alternating signs, so we don't have the -1 to the n power. And we can always check between individual terms to see what we're doing to get from one term to the next. To get from 3 to 7, it's not an obvious multiplication. There is a way that we can manipulate a fraction to make it work. So that wouldn't be the first thing I would check, though. To add, to get from 3 to 7, it's 4. 7 to 11 is 4. 11 to 15 is 4. So remember, every time we had this common difference between the terms, that value they had in common was going to be a coefficient. But if you check back, it can't be 4n, because 4n would make me have terms of 4, 8, 12, 16, 20. Our first term is 3. So it looks like maybe this whole 4n sequence was just adjusted down 1 unit. And then let's see if that one works. If we plug in 1, we'd get 3. If we plug in 2, we'd get 7. Plug in 3, we'd get 11. So that's it. That's perfect. 4n minus 1. For the next one, we have negative 1/2, 1/4, negative 1/8, 1/16, negative 1/32. Anytime you're dealing with fractions, it's usually easier to look for a pattern just among your numerators and your denominators individually. So in my numerators, I'm just going to consider those negatives to be part of the numerator. Our numerators are just flipping back and forth between positive and negative 1, and it starts with negative 1. So that means we're going to have negative 1 to the n. That will start us with negative 1. Now in the bottom, we're going from 2 to 4, and there's lots of ways to do that. But whatever way we choose has to work for every single term. So it also has to get us from 4 to 8. So you could say, well, to go from 2 to 4, I'm adding 2. To go from 4 to 8, I'm adding 4. So that tells you we're not dealing with a common difference. We're not dealing with just a linear expression. So the other way we could get from 2 to 4 is by multiplying by 2. 4 to 8, multiply by 2. 8 to 16, multiply by 2. So we've got a common ratio between those denominators. And we said when we saw that, we would know that that common ratio was going to be the base for an exponential. And then you should always check before you decide this is going to be your final answer. Check the whole thing together. If you plug in 1, you're going to have negative 1 over 2. Yep. Plug in 2, you're going to have positive 1 over 4. Yep. Plug in 3, you're going to have negative 1 over 8. Yep. So it's going to work.